Hello. Tonight, we will discuss the mysteries of dark matter. In the early 20th century, astronomy entered a golden age of discovery. Telescopes grew stronger, and mathematical tools became more refined. As astronomers peered into the heavens, measuring the rotation of galaxies and the motions of stars, something strange became apparent. The numbers didn't add up. Swiss astronomer Fritz Zwicky, working at the California Institute of Technology in the 1930s, made one of the first bold observations that hinted at the existence of something unseen. He studied the Coma Cluster, a large group of galaxies bound together in a gravitational dance. Using redshift measurements, Zwicky calculated the velocities of the galaxies within the cluster. These galaxies were moving far too fast to be held together by the visible mass alone. Based on Newtonian mechanics, they should have scattered into space long ago. Many considered his methods crude, his language blunt, and his ideas speculative. It would take decades and far more evidence before the scientific community began to take the notion of dark matter seriously. The modern story of dark matter truly took shape in the 1970s. Astronomer Vera Rubin, working with W. Kent Ford, made a groundbreaking observation. While studying the rotation curves of spiral galaxies, plots of orbital velocity versus distance from the galactic center, Rubin found something startling. According to Newtonian dynamics, stars farther from the center of a galaxy should orbit more slowly, much like planets farther from the sun. But Rubin's data told a different story. Stars in the outer regions of galaxies were moving at the same speed as those closer in. There was no drop-off in velocity. This implied that something unseen and massive was surrounding galaxies, providing additional gravitational pull. Rubin's meticulous work, grounded in careful observation and data analysis, gave strong credence to the existence of dark matter. Unlike Zwicky's rough calculations, Rubin's findings were clear, repeatable, and persuasive. The astronomy community began to acknowledge that most of the universe's mass was invisible. Despite decades of indirect evidence, dark matter remains one of the greatest enigmas in modern physics. It neither emits nor absorbs light, nor any other form of electromagnetic radiation. It does not interact with ordinary matter through electromagnetic or strong nuclear forces. Its presence is known only through its gravitational effects. The leading hypothesis is that dark matter is composed of non-baryonic particles, not protons or neutrons, but entirely new particles beyond the standard model of particle physics. These hypothetical particles must be stable, cold, moving slowly, and abundant. Several candidates have emerged. WIMPs, weakly interacting massive particles, one of the most studied candidates. These particles would interact via gravity and the weak nuclear force. Axions, extremely light particles theorized to resolve problems in quantum chromodynamics. Sterile neutrinos, hypothetical heavier cousins of neutrinos that interact only via gravity. Machos, massive compact halo objects, includes brown dwarfs, black holes, and other massive objects that are hard to detect, though later studies largely ruled them out as a major component of dark matter. Despite exhaustive searches, none of these candidates have been conclusively observed. Yet the gravitational pull of dark matter continues to shape galaxies, influence cosmic structure, and dominate the mass budget of the universe. To understand the distribution of dark matter, astronomers turn to the large-scale structure of the universe. Galaxies are not randomly scattered, but form a cosmic web of filaments, sheets, and voids. These patterns reflect the distribution of dark matter. Cosmologists use techniques like gravitational lensing to map this invisible scaffolding. Light from distant galaxies bends as it passes through massive objects, including dark matter concentrations. By studying how light is distorted, researchers reconstruct the presence and structure of mass that otherwise cannot be seen. One of the most famous examples is the Bullet Cluster. This pair of colliding galaxy clusters revealed a striking separation. The hot gas, detected via X-ray telescopes, lagged behind the galaxies, while the gravitational mass, mapped through lensing, aligned with the galaxies rather than the gas. This indicated that the majority of mass in the cluster does not interact with normal matter in the usual way. It was among the strongest pieces of observational evidence for dark matter's existence and behavior. These lensing studies, combined with data from the Cosmic Microwave Background, CMB, helped researchers build a clearer picture of the universe's composition. The Planck satellite's high-resolution measurements of the CMB, for example, show fluctuations in early cosmic density that imply about 27% of the universe is dark matter. Only about 5% is ordinary matter. With the growing mountain of observational evidence, cosmologists began building simulations to test their theories. One of the most ambitious was the Millennium Simulation, carried out by the Max Planck Institute for Astrophysics in 2005. Using over 10 billion particles, the simulation tracked the formation of cosmic structures under the influence of dark matter. The resulting structures, cosmic filaments, galaxy clusters, and voids, mirrored the large-scale structure of the real universe. Simulations like this reinforce the idea that dark matter is essential in shaping the cosmos. Without it, the universe would look vastly different. Galaxies would not form as observed, and the web-like pattern of structure would not exist. Further simulations, such as the Illustrious Project and Eagle, added baryonic physics, ordinary matter, and feedback from stars and black holes. These models aim to refine the role of dark matter in tandem with galaxy formation and evolution. These efforts, computationally intense and scientifically intricate, demonstrate how vital dark matter is to explaining not just galaxy motions, but the very formation of the universe's visible architecture. As evidence grew from astrophysics, experimental physicists began designing detectors to catch a dark matter particle directly. One strategy: build large, shielded underground detectors and wait for dark matter to interact with ordinary matter. In Italy's Gran Sasso laboratory, the Dama Libra experiment reported an annual modulation in its signal, which they interpreted as a possible dark matter interaction. However, the result remains controversial and has not been replicated. Meanwhile, Xenon 1T, Liux Zeppelin, and other noble liquid detectors seek rare interactions by watching for faint flashes or ionizations in massive tanks of xenon or argon. Space-based efforts also join the hunt. The Alpha Magnetic Spectrometer, AMS-02, aboard the International Space Station looks for excess antimatter that might result from dark matter annihilations. Ground-based experiments like Veritas, HESS, and the Fermi Gamma Ray Space Telescope look for similar high-energy signatures. Despite decades of effort, no dark matter particle has been detected directly. Yet the search continues with ever-increasing sensitivity. While experimentalists build detectors in mountains and space, theorists work to understand what dark matter could be within the framework of particle physics. The Standard Model, though successful in explaining the known particles and their interactions, does not account for dark matter. This opens the door for new physics and bold ideas. One prominent extension is supersymmetry, SUSY. This theory proposes that every known particle has a heavier superpartner. Among these superpartners, a neutral, stable, weakly interacting particle, often the neutralino, is a prime dark matter candidate. Though elegant, SUSY has yet to be confirmed, even at high-energy experiments like those at CERN's Large Hadron Collider. Another theory involves axions, ultralight particles originally proposed to solve problems in quantum chromodynamics, QCD, the theory of the strong nuclear force. Axions, if they exist in sufficient abundance, could form a type of cold dark matter and fill the universe in a ghostly low-energy background. A third theoretical candidate is the sterile neutrino, a right-handed version of the neutrino that does not interact via the weak nuclear force. This particle could be a warm dark matter candidate and may even tie into the mechanisms behind neutrino mass and the asymmetry between matter and antimatter in the early universe. Though each candidate brings its own advantages, none has yet been detected, and competing results from different experiments continue to muddy the waters. Still, these ideas have spurred entire subfields of theoretical research, with dark matter driving much of modern cosmology and particle theory. Dark matter not only explains the structure of galaxies, it is likely a prerequisite for their very existence. In the early universe, normal matter was too hot and energetic to clump together into stars or galaxies. But dark matter, not interacting with radiation, began forming gravitational wells. As the universe cooled, ordinary matter fell into these wells, eventually forming the galaxies we see today. Simulations show that without dark matter, galaxies would have struggled to form on the timescale allowed by the age of the universe. Moreover, the halos of dark matter surrounding galaxies appear essential to their long-term stability. Without this extra mass, galaxies might spin apart, collapse, or drift away from their satellite systems. Even dwarf galaxies, small collections of stars often found orbiting larger galaxies, appear to be dominated by dark matter. Observations of their motions suggest mass-to-light ratios much higher than that of typical galaxies. These systems serve as natural laboratories for studying the effects of dark matter in isolation. In galaxy clusters, dark matter provides the glue that holds hundreds or thousands of galaxies together. The gravitational influence of dark matter even affects how clusters merge, how hot gas is distributed, and how lensing occurs in the background of these vast systems. Dark matter is more than an invisible mass. It is a framework on which the luminous universe is built. As dark matter continues to evade direct detection, some researchers have explored radical alternatives. Could the laws of gravity themselves be incorrect? One such proposal is modified Newtonian dynamics, MOND, first introduced by Mordechai Milgram in the 1980s. MOND suggests that Newton's laws break down under very small accelerations, such as those found on the outer edges of galaxies. In this regime, gravity weakens more slowly than Newton's law predicts, which could explain the flat rotation curves of galaxies without invoking unseen mass. Other frameworks like TVS, tensor vector scalar gravity, and modified gravity MOG expand on MOND, using relativistic formulations, attempting to retain compatibility with Einstein's general relativity while changing how gravity behaves on cosmic scales. While some of these models can replicate specific galactic phenomena, they generally struggle to explain the full suite of cosmological evidence, particularly the cosmic microwave background and large-scale structure formation. As a result, dark matter remains the leading explanation, but the mere existence of alternatives underscores how mysterious the true nature of the universe still is. The story of dark matter is not told through a single line of evidence, but through a rich tapestry woven from multiple observations across time and space. One of the strongest pillars comes from the cosmic microwave background, CMB, the afterglow of the Big Bang. This ancient radiation, mapped with great precision by satellites like WMAP and Planck, contains tiny fluctuations that reflect the density variations of the early universe. These variations became the seeds of galaxies, clusters, and large-scale structure. By analyzing the angular scale and power spectrum of these fluctuations, cosmologists can infer the composition of the universe. The results are stunning. About 68% of the universe is dark energy, 27% is dark matter, and only 5% is ordinary matter. This so-called LCDM model, lambda cold dark matter, is the standard model of cosmology. Large-scale galaxy surveys, such as the Sloan Digital Sky Survey, SDSS, provide further support. These surveys map the positions of millions of galaxies, allowing scientists to study how structure evolved over cosmic time. The patterns observed match simulations that include cold dark matter and fail without it. Even the baryon acoustic oscillations, relic sound waves from the early universe, leave subtle imprints in galaxy distributions that align with the predictions of a dark matter-dominated cosmos. Together, these clues form a coherent picture. Dark matter is not a patch or fix. It is an essential component of the universe's story. While the nature of dark matter remains elusive, its investigation has spurred the work of some of the most brilliant minds in modern science. Their contributions have formed a chain of discovery stretching nearly a century. Fritz Zwicky, often remembered for his abrasive personality, was nonetheless a pioneer, proposing dark matter decades before it gained traction. Vera Rubin, through her groundbreaking work on galactic rotation curves, provided observational proof that revolutionized astronomy. Her legacy is both scientific and social, as she also broke ground for women in science. Sandra Faber and J. Richard Fisher contributed key work on galaxy formation and dark matter halos. James Peebles, winner of the 2019 Nobel Prize in Physics, developed critical theoretical frameworks for cosmology, including dark matter's role in structure formation. Lisa Randall, a Harvard physicist, explores the idea that dark matter could involve hidden dimensions and novel particles, blending particle physics and gravity. Countless experimental physicists and engineers, from those designing the Elux Zeppelin detector to those calibrating the AMS-02 spectrometer aboard the ISS, continue this global effort. Beyond individual galaxies, galaxy clusters, the largest gravitationally bound structures in the universe, offer crucial insights into dark matter. Clusters contain thousands of galaxies, vast amounts of hot gas, and, crucially, far more mass than visible matter can explain. Observations in X-rays via telescopes like Chandra reveal hot intracluster gas, but the visible mass still falls short. Only when dark matter is added to the equation do the masses balance. Even more compelling is gravitational lensing. Clusters act as cosmic lenses, bending and distorting the light of galaxies behind them. This bending depends solely on mass, visible or not. Detailed lensing maps of clusters like Abel 1689 and the Bullet Cluster reveal the gravitational signature of dark matter. In these cosmic collisions, the hot gas, detectable in X-rays, slows down and lags behind. But the majority of the mass, inferred from lensing, moves unimpeded, just as dark matter should. These observations strike a powerful blow against theories that propose modified gravity in lieu of dark matter. To understand dark matter's full role, one must examine the very earliest moments of cosmic history, within the first few 100,000 years after the Big Bang. During this era, matter and radiation were tightly coupled, forming a hot, dense plasma. As the universe expanded and cooled, photons decoupled from matter, giving rise to the cosmic microwave background. Dark matter, however, followed a different path. Because it does not interact electromagnetically, it began to clump earlier than ordinary matter, forming gravitational wells that would later attract normal matter once the universe became transparent. This early structure formation explains why the universe today contains galaxies, clusters, and large-scale cosmic filaments. Without dark matter's quiet and invisible influence, there would not have been enough time for these massive structures to form from ordinary matter alone. Cosmologists use the epoch of recombination, when electrons combined with nuclei to form neutral atoms, as a reference point. The density and distribution of matter at that time, including dark matter, influenced the size and shape of CMB fluctuations. These imprints help confirm that dark matter was present, stable, and non-relativistic, i.e., cold, in the early universe. The quest to detect dark matter continues with renewed energy. Around the world, collaborations are building ever more sensitive instruments in the hope of catching a glimpse of the elusive particles that make up this hidden mass. Underground detectors, Lux Zeppelin LZ, located in South Dakota. This next-generation detector uses a massive tank of liquid xenon to look for rare WIMP interactions. Xenont. Based in Italy's Gran Sasso laboratory, it is one of the most advanced dark matter detectors, designed to detect extremely faint signals. Space missions. AMS-02 continues to operate aboard the ISS, measuring cosmic rays and searching for signatures of dark matter, particle decay, or annihilation. Euclid, a European Space Agency mission launched to map the geometry of the dark universe, aims to investigate both dark matter and dark energy through galaxy surveys and gravitational lensing. Future prospects. Darwin, a proposed European detector, could provide sensitivity beyond any current generation. The Cherenkov Telescope Array, CTA, will search for gamma rays from potential dark matter annihilation in galactic centers. Although results have so far been negative, each null detection helps narrow the search and refine theoretical models. The absence of detection is itself a clue, telling scientists what dark matter is not, and thereby sharpening our understanding of what it could be. The search for dark matter is more than a technical challenge. It speaks to the limits of human perception and knowledge. For centuries, astronomy has evolved from naked eye observations to telescopes that reveal invisible wavelengths. Now, it has extended to phenomena that interact only through gravity. Dark matter is a reminder that the universe is far stranger than imagined. It raises fundamental questions. If 85% of matter is dark, what does that mean for our understanding of mass, forces, and the evolution of the cosmos? It also reframes humanity's place in the universe. The matter that makes up stars, planets, and people is only a tiny sliver of existence. The vast majority is composed of something that does not shine, cannot be touched, and remains stubbornly hidden. As science progresses, answers may come not just from physics or astronomy, but from new fields entirely. Perhaps quantum gravity, string theory, or technologies not yet imagined. The effort to solve the dark matter mystery may ultimately reshape our entire scientific worldview. A difficult but essential question lingers. What if dark matter remains undetectable? For decades, science has built up a framework based on indirect evidence. But if dark matter never interacts through any force but gravity, how will researchers ever identify it conclusively? This dilemma invites serious scientific reflection. In the past, ideas that once seemed immovable were eventually overturned, from the geocentric model of the solar system to the assumption that atoms were indivisible. Could the same happen with dark matter? Several possibilities exist. Dark matter may not be made of particles at all, but instead be some new aspect of space-time geometry, an emergent property, a modification of gravity, or something entirely unexpected. It might be hidden in a dark sector, complete with its own forces, interactions, and complexity, invisible to us not by accident, but by design of the universe. Or perhaps our methods of detection have simply been aimed in the wrong direction, using the wrong materials, looking in the wrong energy range, or relying on assumptions that do not hold true. Failure to detect dark matter wouldn't invalidate its existence. The evidence for its gravitational effects is too strong, but it would call into question many assumptions about what it is. That would open the door to transformative new physics, possibly leading to the discovery of principles as revolutionary as quantum mechanics or relativity. Though distinct from dark energy, dark matter plays an essential role in helping scientists study the acceleration of the universe. While dark matter causes structures to clump and grow, dark energy drives them apart by accelerating cosmic expansion. Instruments designed to study dark energy, such as the Euclid mission, the Vera C. Rubin Observatory, and the Nancy Grace Roman Space Telescope, must precisely measure the distribution of matter over time. Since dark matter shapes that distribution, understanding it is necessary for understanding how dark energy behaves. Moreover, some theories propose that dark matter and dark energy could be connected, perhaps different manifestations of the same phenomenon, or components of a hidden sector interacting through unknown forces. This possibility has sparked new branches of research, exploring whether dark matter decays into dark energy, whether a scalar field underlies both, or whether the two could have influenced the early universe's symmetry-breaking events. As more data rolls in from next-generation telescopes and surveys, scientists hope to unravel how these two great cosmic mysteries might be linked, or whether they are entirely independent but equally elusive. Some of the earliest theoretical candidates for dark matter weren't exotic particles, but rather primordial black holes, hypothetical black holes formed just after the Big Bang. Unlike stellar black holes, these could have originated from high-density fluctuations in the early universe and might be as small as an asteroid or as large as a star. Primordial black holes could behave like dark matter, massive, non-luminous, and interacting only gravitationally. However, searches for their gravitational lensing effects and microlensing signatures in the Milky Way have largely ruled out their dominance in most mass ranges. Still, black holes remain closely linked to dark matter in astrophysical research. Some theories propose that dark matter could concentrate around black holes, affecting their growth or producing detectable signatures through particle interactions near the event horizon. Furthermore, gravitational wave detectors like LIGO and Virgo, which detect black hole mergers, might also uncover clues about dark matter if unusual mass distributions or merger rates emerge that cannot be explained through ordinary stellar evolution. This area, bridging general relativity, astroparticle physics, and cosmology, reflects the deepening complexity of modern science as it explores the interplay of invisible mass and extreme gravity. In the absence of direct detection, computer simulations have become one of the most powerful tools for studying dark matter's role in the cosmos. By encoding the laws of physics and initial conditions from the early universe, researchers can simulate how structures should evolve over billions of years, with and without dark matter. Projects like the Millennium Simulation, Illustris, and Eagle have rendered incredibly detailed virtual universes. These models include dark matter as a scaffolding upon which galaxies form and interact. When dark matter is removed from the simulation's large-scale structure, the cosmic web of galaxies and voids simply does not form in time. These simulations also help scientists interpret observational data. For instance, they can test whether a given dark matter distribution would produce the observed galaxy rotation curves, lensing patterns, or galaxy cluster dynamics. They also predict dark matter subhalos, smaller concentrations of dark matter that should host dwarf galaxies or satellite systems. Moreover, simulations allow researchers to explore different types of dark matter. Cold dark matter leads to dense, clumpy halos and well-formed galaxies. Warm dark matter, slightly faster-moving particles, tends to smooth out small-scale structures which could help explain some missing satellite problems. Self-interacting dark matter may create cores in galaxy centers instead of cusps, potentially resolving discrepancies between models and observations. As computational power increases and more sophisticated baryonic physics is added, these simulations will offer ever sharper insights, not just into dark matter's role, but into how galaxies form, merge, and evolve. Despite its abstract nature, dark matter has entered the public consciousness. It appears in books, documentaries, sci-fi films, and even art installations. The idea of invisible mass has become a metaphor for mystery, for the hidden depths in both the universe and the human mind. Movies like Interstellar and The Dark Knight Rises make passing reference to the mysterious substance. In literature, dark matter often symbolizes the unknown, the unreachable, or the barely understood. Even in philosophical or theological discourse, some writers use dark matter as an analogy for hidden forces or divine mystery. In educational settings, dark matter has become a common gateway topic to engage young learners in physics and astronomy. Its elusive nature makes it a compelling challenge and sparks curiosity, a mystery that invites participation in the ongoing quest for knowledge. Meanwhile, artists and designers have used dark matter as inspiration for visual representations of invisibility, tension, and gravity. It has even been used metaphorically in psychology to represent unconscious thought or trauma, hidden, yet shaping everything around it. The cultural resonance of dark matter reflects the human urge to understand what lies beyond immediate perception, to illuminate the darkness, whether literal or metaphorical. Looking forward, the search for dark matter is accelerating. With new telescopes, underground laboratories, satellites, and theoretical models, science stands on the cusp of a potentially paradigm-shifting discovery. Key initiatives. The Vera C. Rubin Observatory, with its Legacy Survey of Space and Time, LSST, will map the sky in unprecedented detail and may spot the gravitational effects of dark matter on transient events and faint objects. The DarkSide 20K experiment aims to scale up liquid argon detection for better sensitivity to dark matter interactions. Next-generation gravitational wave detectors may reveal indirect signs of dark matter through unusual black hole dynamics or mergers. Theorists are also expanding their horizons. Some explore hidden valleys, fifth forces, or connections between dark matter and the inflaton field that drove cosmic inflation. Others are examining the neutrino portal, which posits that dark matter might interact via new physics related to the mysterious neutrino masses. Ultimately, the hope is for a unified framework, one that not only identifies what dark matter is, but explains why it exists, how it formed, and how it fits within the larger tapestry of nature's forces and particles. Whether the answer comes from a particle in a detector, a fluctuation in a survey, or a revision of our understanding of gravity, it will reshape science in profound ways.